8:33 already. It's just 8:33 already. Amazing. I forgot my glasses. Second time. Damn. Well, no one's sitting in the far back, except for this. I don't know. It's hard to tell. Hard to tell whether it's okay if you start a minute early. Oh. Oh yeah, yeah. Oh yeah. No, no, I don't you worry, I'm aware. Okay. So let's get started. So welcome back, everyone. Hello. Welcome back, everyone, to Comp 330. This is lecture 14. How time flies. It's already lecture 14. Sorry, how many? I think there's 25. So we're past the halfway mark, which makes sense, past the midterm. That's why it's called that. So before we get started, another Italian expression. Today it also has to do with the Pope, and it also has to do with the Pope dying. So today's Italian expression is morto un papa, se ne fa un altro. The direct translation of which is when a pope dies, another one is elected. So, popes are replaceable. But this is actually used to mean something like, life goes on. So if an Italian wants to say something like life goes on, they say morto un papa, se ne fa un altro. So what's a sentence in which I can use this expression and it's somewhat relevant to you? In this case, it's not very relevant. This is my sentence. Whenever Cesare isn't satisfied with the cleverness of his Italian expression sentence, he tells himself, morto un papa, se ne fa un altro. A very meta sentence this time. Okay, so on to slightly more serious announcements. I'd just like to remind the people who are writing the makeup midterm that it is scheduled for October 26th. Although many of you who I know are taking the makeup aren't here. So hopefully you'll watch the recording before October 26th. And it's scheduled for 8:30 a.m. So unfortunately it had to be scheduled during class time because there weren't any other non-conflicting times. And it's in McMed 325. So sorry about that. It's an even steeper walk than usual in the morning. Okay, the other thing I want to say is that the midterm evaluation is out. So I released it on Tuesday. So I ask you, three straightforward questions. What do you like about the class? What you don't like? And if you have any concerns or suggestions. There is already one concern which has been stated a few times, and I'd like to put it to rest already. So someone or a few of you were saying that because the midterm was so quote unquote easy and because people did so well, I was going to make the final insanely hard. Does that sound like something I would do? No, right? So the final will be just as fair as the midterm. My goal is not to sink you in the final. If everyone gets an A-, then I'll be extremely happy. Nothing will make me happier, actually. Well, some things. Pizza makes me happy, but anyways. The other thing is that I was going to announce that assignment 3 was due tonight, but I've talked to some of you, and what I'll do is I'll make it due tomorrow. So I'll make it due tomorrow night. And I will release assignment for tomorrow, and I will make it due on Friday, not Thursday. So it will be due on Friday at midnight. So if some of you had plans on Friday night, I'm sorry, but it's midterm season, so hopefully you don't have that many plans. Good. Okay, I feel like there was something else I wanted to say, but I can't remember. Well, it's not here, so it probably wasn't that important. Okay, hello. Good. So, any questions about logistics or these announcements? No? Okay, good. All right. So we can move on to the actual material for today's class, which will be a continuation of grammars. So I'll write grammars continued. Okay, so just a reminder, what are grammars? Grammars are language generators. The other comment in the midterm evaluation was that my handwriting is not very legible. So I'll try to work on that, but it's difficult to adjust midway. So grammars are language generators. They generate strings. So far we've only been dealing with language acceptors and language describers, but this is sort of a slightly different paradigm. And we saw on Tuesday different types of grammars, and based on the expressiveness of their production rules, so that's what determines the type of the grammar, you have different classes of family of languages, which can be generated by different types of grammars. And so, for instance, we had the family of languages generated by right linear grammars, which was a proper subset of the ones generated by context-free grammars, which was a proper subset of the ones generated by context-sensitive, which was a proper subset of the ones generated by unrestricted grammars. And so for today, we're going to focus most of our attention on the family of languages generated by context-free grammars, but we're going to start with a warm-up exercise and talk about right linear grammars. And so let's do that right away. Let's look at the warm-up exercise. So in this warm-up exercise, we're asked to determine the language generated by the following right linear grammar. Right linear grammar, let's call it G. And let's say that G is a four-tuple. In this case, it has 3 variables. It has S as its start variable, as is the convention. Its set of terminals are AB, and its set of production rules are listed here. So there's 3 variables, and so I'm going to have 3 lines of production rules. I'm going to have the production rules for S. So S gives me AB, S, or A. And then A gives me BB, A, or BB, B. And then B gives me CCB, C, and CS. Okay, so remember, a right linear grammar is a grammar where all the production rules look like some string of terminals and then either a variable or just the empty string, right? And so that's what we have here. If we look at all of the production rules, all of the bodies of the production rules, I have strings of terminals, and then I only have a single variable, at most one variable to the right. Yeah. So it's to the right, that's why it's called a right linear grammar. There's also something known as a left linear grammar, and it can be shown that left linear and right linear grammars are equivalent in expressiveness. But in this exercise, we're focusing on right linear grammars, and what we want to do is we want to determine what the language generated by the right linear grammar is. So how am I going to do this? Well, I know that the way that my grammar generates, yeah, is there a mistake? Oh, yes, absolutely. Thanks very much. Yes, absolutely. Very good. Thank you. Yes, C should be in T, right? There's a small typo here. I have these terminals. I'm claiming the terminals, but if they are terminals, they should be in T. Thank you. Thanks very much. Okay, good. So how does my grammar generate strings? Well, for it to generate any string, it has to start from the start variable S. And then from the start variable, what my grammar does is it replaces the variable S with one of the bodies to the right-hand side of these production rules. So suppose now my grammar wants to generate some ABs. So it'll replace S with ABS. So it replaces S with ABS. And now it's back to the start variable. Okay. So now maybe it wants to generate a few more ABSs. So it can do maybe another replacement of ABS, and maybe a third. And in general, my grammar can, in 0 more steps, derive a string of intermediate form that looks like ABN S for some n greater or equal to 0. And so we'll see why it's greater or equal to 0 in a second. Well, I guess strictly, let's just say n, and then let's talk about what the bound on n is. Okay. So S can generate a sequence of ABs, and then the variable S. And then at some point, the grammar decides, oh, actually, I want to stop generating ABs. I want to go to A. So I'm going to go to A and start generating strings from this line. So I'm going to jump to the variable A, right? So remember, I'm not putting a bound on n quite yet. I'll do that at the end because then it'll make a bit more sense. So now I've jumped to A. And now what A can do is it can either take this production rule and stay at itself, right? Stay at itself, meaning stay at the variable A, or go to the variable B by generating BB. So if it takes this production rule, it can do this any number of times. And so then in general, it can generate a string of the form. You can generate from S a string of the form ABN, BBK, let's say A. Again, I'm not putting bounds on n and k yet. You'll see why in a second. Okay, so I know that from S, I can generate ABs, and then I can jump to A and then generate BBs. Okay, that's all that's going on. Okay. Okay, then at some point, my grammar does need to jump. It does need to jump to B, because remember, the grammar has to generate a string of terminals. So this isn't a string of terminals because I have at least one variable, in this case, A in it. So at some point, I need to jump to B. To jump to B, I need to generate BB. So I need to generate at least one pair of BBs. That means to get to B. So then that means that I'll have a string of this form. Okay. So now I'm at B. Now I'm at the variable B. And now what can happen? Well, I can generate pairs of C's, right? I can generate pairs of C's. So I can generate any number of pairs of C's. So let's say CCM. And then if I want to terminate, so let's move this just a bit to the left. If I want to terminate, the only option I have is to generate this final C, right? So to replace this B here with a final C here. Okay. So I can stop my generation by replacing the B with a C. Okay. And so then I would have a string of this form, ABN, BB, I guess there's a typo here, BB whole K, CCMC. Okay, so this is one possibility. Or the other thing I could do is I could say, well, actually, I want to do this all over again because it was so much fun, right? So I'm going to say, okay, I'm going to generate the C and go back to S, right? And then once I'm back at S, I have to go over the same process. Because if I want to get just the string of terminals, I have to end back at the production rule B gives me C, right? That's the only way that I can terminate in this case. So that means in general, my language generated by G can actually be denoted quite compactly using a regular expression. That's what I'm going to do. I'm going to represent it using a regular expression. So it's going to be a sequence of ABs and then a sequence of pairs of Bs with at least one pair of Bs, and then a sequence of pairs of Cs with at least one C, and then all of this whole star because it can repeat any number of times. And so you'll notice that I was saying at the beginning that I didn't want to talk about the bounds on N, K, and M. And that's just because now at this point, you can see that if you start at S, you can either opt to go directly to A, in which case N could be 0, or you could generate a number greater or equal to 1 of ABs, right? In this case, however, you need to have at least one pair of BBs, so that's why this is encoded here. And then in this case, you could have any number of pairs of Cs, but you have to have at least one sort of dangling C here. Okay. Okay. So there's a mistake here though. What's the mistake? Yeah. Yes, excellent, very good. The mistake is that the sequence has to happen at least once, right? Why? Because from S, I can't generate the empty string, right? There isn't this production rule. So then this thing has to happen at least once, meaning that the regular expression would need to look like, and this is the convenience of having an iPad, something like this without the star, right? So this concat this. Okay, good. Let me just clean this up with the brackets. Let's say this is a bracket. Okay, good. Yeah.
Doesn't there need to be one C on the outside? Because here it's many times it goes to CS, but there's a terminal C, which is not included in the.
No, I don't think so. I don't think so. This is no, this is right. This is right. No, you have to think about why what you're saying doesn't quite make sense. Yeah. Good. Okay. All right. So hopefully you've been warmed up. This was the warm-up exercise. Now let's do a slightly trickier exercise, because what we've been doing so far is, I've made some claim here about what the language generated by G is. I've said it's the language denoted by this regular expression. But even on Tuesday, I was making these claims without real proof. And for the most part, that was okay because the grammars were pretty intuitive and pretty clear to begin with. But you'll see that for some slightly more complicated languages that require slightly more complicated grammars, it's less obvious to see why exactly, or it's less obvious to claim without proof that the language generated by G is a particular L. And so what I need to do then is I need to introduce a new proof technique. And this proof technique will be about formally showing that some language L is in the family of context-free languages. So this technique works just as well for right linear grammars or for regular, for showing that a language belongs to the family of languages generated by right linear grammars, and also context-sensitive and unrestricted ones. But for our purposes, we're going to focus on context-free languages, and in particular, the family of languages generated by context-free grammars. So what I want to show is I want to formally show that some language L is in this family of languages. Okay. And so to do this, what I need to do is I need to first design a context-free grammar G such that the language generated by G is L. Okay. And then I need to prove the correctness. I need to prove the correctness of G. Okay, so this is the sort of new thing that we're going to do now. We've already been designing grammars, and most of them have been context-free so far. So right linear grammar is a context-free grammar. So actually, all of them have been context-free so far. The new thing really is proving the correctness of a particular grammar. Okay, and so the way this works, is by induction, of course. So this is actually by induction, and it's actually going to be by strong induction. So someone asked me in lecture 1 whether we need strong induction, and then I mistakenly said no. No, in fact, you do need strong induction. We're going to use it right here. Okay, and so I want to claim that the grammar G is correct. So I want to show that L of G is truly equal to L. So then to do that, I, of course, need to prove this by double subset inclusion. So I'm first going to show that if some string is generated by G, then it's an L. To do this, I will do induction and strong induction, that is, on the number of derivation steps. And in the second case, when I'm trying to show that if some string, is an L, then it must be generated by G. In that case, I'm going to do induction on the length of some string W in L. Okay, that's what I'm going to do. So this is a proof technique. Now, to illustrate this, I'm going to do another example. And this example is quite important. So the example here is to show that the following language L, where L is a language containing strings over the alphabet AB, where those strings have the same number of A's as B's. Okay. So we saw during the pumping lemma lecture that this language is not regular. It's not regular because, suppose it was intersected with A star B star, you get A and Bn, right? And A and Bn is not regular. Okay. But it turns out it is context free. You can create a grammar that generates it. And we'll see how to do that in, well, not in a second, right now. Okay, so let's design a grammar. So the first thing we need to do, right? So the first thing we need to do to show, well, I guess this is missing the end of the sentence. So what do I need to do? I need to show that L is context free. So the first thing I need to do is I need to design a context free grammar G such that it generates L. And then the second thing is I'll prove its correctness. Okay, so I'm going to use the same technique I've been using on Tuesday, where I'm going to talk about this language recursively and then try to map this recursive nature to the grammar. So if I'm thinking recursively, what's a base case and the only base case for a string to be in this language L? Empty string, very good. So the base case is the string has no A's and no B's. Yeah. Sorry. Oh, yeah. Oh. No problem. That's not even better. Let's just minimize it. Okay. All right. Yes, very good. Thank you, Louis. So the base case is you have no A's and no B's. So of course you have the same number because they're both 0. So the base case then can be encoded as S generates the empty string. Now the recursive case is trickier. And it's actually, I would say, much trickier than the previous examples we've seen, because you can't assume a form for the string W, right? So, W could be AABB. So this would be an L. But W could also be, it doesn't have to start with A's. It could start with a pair of B's. Then those pairs of B's could be matched with 2 A's. Then you could get another A, match that with a B, then another B, match that with an A. So that's also an L. Okay. But there is some recursive pattern here. We just have to discover it. And to discover it, we're going to use a very nice trick. It's very exciting. I love this trick. It's amazing. We're going to do something very cool where we plot something. Okay, so we're going to do a plot. Okay, so to do a plot, I first have to say something. So let's imagine for a second that I have some string W in L. So now, what should W look like? Well, W should just look like a sequence of letters. So let's sort of write that down explicitly. Let's say the first letter is sigma 1, the second letter is sigma 2, the third one is sigma 3, and this goes all the way to sigma 2k minus 1, sigma 2k, for some k greater or equal to, let's say 1, because we already covered the base case. Okay. So why is it 2k? Why can I say it's 2k? Am I losing any generality by saying it's 2k? No, why not? Yeah, you see, you need the same number of A's and B's, right? So then the length of W is NA plus NB, but then NA is equal to NB, so you get, 2NA, right? And that's clearly even, so I have that the length of W is even, okay? So then I don't lose any generality by representing W in this manner. Excellent, good. So now it's time to make a plot. I love this trick, it's amazing. I'm so happy I'm doing this, okay. So let's make a plot. Let's make a plot. And so, of course, maybe I should have also said sigma i's are, AB. So I'm going to make a plot where I'm going to plot the difference of the number of A's with the number of B's versus J. And now it's not quite just going to be the number of A's minus the number of B's. It's going to be the number of A's for some particular substring. So it's going to be for the substring sigma 0 all the way to J. So I'm using, Python slicing, where in this case, though, I'm saying that J is inclusive. So J inclusive. Okay, good. So I'm counting the number of A's from position 0. So position 0 is the position right before the first position. So, at this position, I have no letters, either A's or B's. Then I go all the way to J. So maybe J is here, and then I count the number of A's. So, maybe in this case, there's this one and this one is an A, so that's 2. So I count that, and then I also count the number of B's. So to count the number of B's, I do something like, well, I count the number of B's for the same substring, right? So from 0 to J. And then what I'm doing is I'm plotting this versus J. That's what I'm going to do. Okay. So let's do that. And let's do that with an example. So the example I'm going to write here is, let's say, AABB, BA, and then AAA, BBA, BB. Okay, so this is my example. So let's just quickly number these positions. Yeah, good. It's even, very good. Thank goodness it's even. Okay, now in a plot. So let's make a plot. Hopefully you know how to make plots. Hopefully I know how to make plots. This is not a very straight plot. Okay, so let's see. So let's have 1, 2, 14, very good. Okay, I have enough space, so this is 0. And so I'm doing NA minus NB versus J. Okay, so let's see what happens. So from 0 to 1, what happens? Well, I get 1 extra A, so that the difference is now 1. So I go here, right? So let's say this is 1, 2, and 3, and this is -1, -2. Then I get another A. So at this point, the difference, right? So at this point, I'm here. So at this point, I'm here. And I'm taking the number of A's, so 2, minus the number of B's, that's 0. So I get 2. Right? Then now I have a B, so that makes my graph decrease, right? That makes my curve decrease. So I go here, then I get another B, and that makes my graph decrease again. Okay. Then I get another B, so then at this point, I'm here. At this point, I'm here. But now I have an overflow of B's, so I become negative, right? I become negative. So I go here. But now the A saved me, so I go back to being, well, not positive, but I go back to being 0. Okay. And then again, let's just do this without me sort of making a story out of it anymore. So I go to A, I read 3 A's here, and then I read 2 B's, so I go back down, then I read an A, and then I read a B. Okay, excellent, very good. So this is the plot. Now, at this point, you're probably thinking, what the hell's the point, man? Why are we doing this? So the point is that this sort of showcases a underlying recursive pattern in the string. Because what you'll notice is that every time my curve touches 0, I create a substring that respects the definition of the language, right? So for the substring that goes from position 0 to 4, I have AABB. So that's a string that's in the language because it has the same number of A's and B's, right? And so if I'm taking this leap of faith that recursion usually does, which is that, from S, you can generate some substring with the same number of A's and B's, then you can say, well, that means that S should be able to generate this substring, right? So this substring X. Then again, it should be able to generate this substring Y. So S should be able to generate this substring Y. And then again, S should be able to generate this substring Z. So what this is telling me is that from S, the first type of recursion that could happen, the first type of recursive case is that you could take S and split it into multiple parts. Right? If you're allowed to say that S can derive SSS, then now you've covered the possibility that you can have this first S generate this second S generate this, and this third S generate this. And so it's actually quite easy to encode something like this. All you need to do is you need to add the production rule S gives you SS. If you do this, then you can generate any number of S's, right? You can generate 2, of course. You can generate 2. You can also generate 3. How can you generate 3? Well, you can just say S gives you SS, and then take this S and split it into 2, right? So split it into 2. Okay. And then if you want 4, then you could just take this S, again, split it into 2, right? So you can always add an extra S. Okay, everyone's with me so far? Yeah, yeah. Let me repeat at the end. I'll repeat at the end, because then you'll get the big picture. Yeah, okay. Okay. Because remember, one of the things to remember though is in recursion, you're making a small leap of faith. You're saying, okay, from S, I'm able to do this thing that I want. Okay, that's how recursion usually works. Okay, so this is the first recursive case that's important to consider. The other important recursive case is the actual generation of letters, because at this point, all I'm doing is I'm identifying substrings, right? But I'm not actually generating any letters. I need to generate letters. And so what you'll notice is that there's another recursive pattern that occurs, which is if you take one of these subcurves, one of these subcurves is always above 0, right? Other than at the beginning and at the end. So what that means, if it's always above 0, that means that to start with, it goes up, and then to end with, it goes down. But if it goes up at the beginning, that means that there's an extra A. And if it goes down at the end, that means that there's an extra B that moves it down, right? Because if you read an A, you increase the count. And if you read a B, you decrease the count. Okay? So that means that to generate this portion of the substring, you need some way of generating an A and a B. And then once you can generate this A and this B, you can sort of move this x-axis up. You can move this x-axis up and repeat the same argument on this smaller triangle. So if you can generate this substring, then you move the x-axis up, and then you can generate this substring. Okay, and this is going to work even for this slightly more complicated example. So let's see this. We know that this subgraph, this subplot is always above 0, other than here and here, which means that at the start and at the end, it's going to have an A and a B, so it has opposing letters. So once you're able to handle that case, then you can move your x-axis up. So you can move your x-axis up. And now at this point, it's not quite as easy, right? You can't say, you can't really start matching this A with this B. But what you can do is you can say, let's split this again. Let's split this again into 2 subcurves. This subcurve and this subcurve. This subcurve has an equal number of A's and B's, and so does this one. And so that's what I'm going to do. So that means that to actually generate a string, what I need is the matching of opposite letters. So I need to match maybe this A with this B, and then allow the recursion to deal with the rest, right? So allow the recursion to deal with the rest, meaning that I'm assuming that S can generate the rest of the string, but to opposite sides, I need to generate A and B. And then it's the same thing if I'm below the x-axis. If I'm below the x-axis, for instance, here, then that means that I must have gone down. So I must have read a B, and then I must have gone back up. So I must have read an A, right? So I read a B, and then I read an A. So that's what I'm going to do here. I'm going to say S gives me B, S, and then A. And so then altogether, the grammar G, which should generate L, is amazingly a grammar that has a single variable. That's pretty cool that it's only a single variable, which is, again, the start variable, because the start variable has to be in V. T is going to be a B, of course, because that's just sigma in our case. And then P, the set of production rules are going to be S gives me the empty string, SS, ASB, and BSA. Okay. So this is going to be the grammar that generates the language L. Incredibly. I think this is very incredible. Okay. So do you want me to repeat? Was this okay? Comme ci, comme ça? Comme ci, comme ça. I don't like that. I want it to be more ci than ça. Any concrete questions other than can you repeat? Because I can't really work the problem if it's a repetition. Yeah. There's many ways to do it. This is one way, but let's clear out the way.
Would it be enough to just say, okay, don't do string in a language?
Yeah.
Basically, without all the way to take the way to make a string. Ooh, it's letter longer. Ooh, no, feel like eight, yeah.
I think you have to add kind of. I think that would probably still work. So the question is, can you, but now what you're doing is I think you're making the right thing. You're assuming that S is on the right. And I don't think that's really. No, that's good. Right, so the question, I think the question here is, can you hard code pairs of things? Like pairs of letters, like imagine an A and a B, or right next to each other, to have a B or B is right around the right. I think that could also work. I need to see it written down. I think it might work, but I think this is simple enough. You don't think it's simple? I think that I'm so happy with it. Okay. Maybe you can show me afterwards, and maybe I can post an alternative. Yeah. Yes. Concrete.
What is what do you know that?
Oh, so you know what? Okay, good. So yeah, let's just show an example of that. Okay, good. Okay, good. So let's maybe not generate this one because this is a bit long. Let's say, I don't know, A, B, B, A, B, A. Yeah, this should work, right? Right. So this is a string. So let's see what the grammar would do. Well, it would say, okay, I have this subcomponent and this subcomponent. So S gives me SS, right? Oh, actually, that's not going to work. Hang on. Right. So that one works. So the reason why that's not going to work, right? What I just said is because now at this point you have to have opposing letters, but you don't, right? So the grammar can't do that. So the other way that it can do this, is it can say, well, I'll identify these three, right? Because actually that's what the graph would tell you. It would tell you something like this. Okay. So then it would say S gives you SS, and then maybe replace this S with SS. So you get three S's. So now what you're saying is that S should give you each of these three things. And you can do that, right? So you can do that for the first one. So S gives you ASB, SS, and then you replace the S with the empty string. So you get ABSS. And then again, this S, the second one, generates this pair, right? So BSA. And then you can replace the S with the empty string. So again, you get that. And then this BA here, right? So you do the same thing for this BA here. So you get BSA, and then S can be replaced by the empty string. So you get AB, BA, BA. Yeah? Okay. So you had a question. Yeah. 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 Down and back. Yeah. Very good. Right, so it's not like an exclusive, right? Because you could go up and back down, and then you have to reach the point. Good, excellent, very good. Okay, this is okay. Yeah, yeah. Okay, all right, good. Okay, excellent. So I'm very happy I got to do that. My dream is partially fulfilled. My dream will be completely fulfilled once I talk to you about reductions, which are really fun. Okay. All right. Good. So now, right, this is the grammar. And like I said, at this point, I have this grammar, and now it's sort of, I think, less obvious to just argue in a sort of hand-wavy fashion that it generates the language that I'm claiming it generates. So in this case, I need a proof, and I'm going to do a proof by induction. So this is the second part of this exercise. And it's going to be, so now I need to prove the correctness. I need to prove the correctness of G. Okay, so let's just remind ourselves again what G is. And when I say that, I really mean, let me remind myself. Okay, so this is G. Excellent, very good. Thanks very much. Now, let's start by showing that if a string, so let's start by showing that if a string is generated by G, then it must be in L. Okay, so let's do that. So to do that, I need to make a claim. So I'm going to make a claim that's going to have to rely on the number of steps in my grammar G. And what this claim is going to look like is it's going to look like if S derives W in n steps using the grammar G, and W is a sequence of terminals, then W is in L, right? So this is a statement, and this is clearly a propositional statement, or it's really a propositional function because it relies on this integer n. And so you could say that this is like your statement P of n. Okay. Okay, good. So to prove this, I'm going to have to do this by strong induction. So the proof is going to be by strong induction. You don't always need strong induction, but you do in this case. And so the question is probably going to be, oh, when do you know if you need strong induction or not? You'll know once you get to your inductive step, okay? Because then maybe at your inductive step, your inductive hypothesis is just not strong enough, at which point you have to tell yourself, oh, I probably need to use strong induction. Okay, so let's do strong induction, and then let's do it on n. So remember, this is the statement I'm trying to prove. Okay, so let's do the base case first. In this case, I'm going to do two base cases. It's not obvious why I have to do two base cases at this point, but it's going to be obvious when I do the inductive step. So let's show the base case when n is equal to 1. So that means that I need to show that if in one step, my grammar is able to generate a string of terminals, then W should be in L. But now if we look at our grammar G, what is the only string of terminals that can be generated by G in one step? Max. Empty string, very good. Very good. So by construction, W must equal the empty string, which is, of course, in L. Very good. So that's the base case for n equals to 1. Let's do the base case when n equals to 2. Right? So now I have to think about all of the strings of terminals, right? So that don't include any variables, which can be generated from S in 2 steps. Okay. So if we look at the grammar again, well, clearly the first production rule. So now what I'm trying to do is I'm trying to predict what the grammar would look like, right? So what would its derivation steps look like? So it starts at S. Now, it naturally can't use the production rule S gives me the empty string because that would just use one derivation step. So then it has to use either this one, or this one. So if it uses the first one, that counts as one step. So this is one step. And now at this point here, the grammar can only use one more step. Right? It can only use one more step. So it clearly can't use any of these production rules, right? Because those have variables. And then at that point, at derivation step number 2, you wouldn't have a string of only terminals, you would have a string of terminals and variables. So that means that the only thing I can really use is the production rule S gives me the empty string. So that's what I'm going to do. I'm going to use the production rule S gives me the empty string here. So then in one step, I can get the empty string. Then from here, I can get in one step AB. And then from here, I can get in one step BA. I've made a mistake. What's the mistake that I've made here? Right, very good. It's not true that I can get in one step from SS to the empty string. For that to happen, I would need to have a production rule that looked like SS gives me the empty string. But this is a context-free grammar. This is not a context-sensitive grammar. So this is not good. I guess it wouldn't even be a context sensitive graph because the left-hand side would have more symbols than the right-hand side. So I don't have this. And so to do this, you would actually need 2 steps. So that's no good. So the only thing I can really consider are the strings A, B, and B. And these are both, of course, in the language L, because the number of A's and B's are both 1. So that's the base case. Yeah? Yeah. Base case. Very good. Okay. By the way, if I'm spending this much time on this question, okay. So now I have to do the inductive hypothesis, right? So the inductive hypothesis is what I'm going to assume is true for my graph, right? So the inductive hypothesis I'm going to state is going to be one that uses sort of a strong a premise. So it's going to sort of strongly assume something. That's why I'm using strong induction. Well, no, that's not why I'm using strong induction. That didn't make any sense. Let me just write the inductive hypothesis and then you'll see. Okay. So the inductive hypothesis says that for some n in the set of natural numbers, where n is at least 2, and for every k, which is a natural number, and k is between 1 and n, we have that if S derives W, a string of terminals, so W is a string of terminals, with the grammar G in k steps, then W is in L. Okay. So this is strong induction because I'm claiming a range over k, right? So I'm not just saying it's true for n, I'm saying it's true for k from 1 to n. And so notice here that this lower bound is for n greater or equal to 2. That's okay because I've shown the base case for 1 and 2. Okay, so now I need to show this for n plus 1. So in the inductive step, I need to show for n plus 1, which really means that I need to show that if S derives W in n plus 1 steps using grammar G, then W is in L. So this is what I want to show. This is what I want to show, and this is what I will assume. So I will assume this. Okay, good. Okay, so this is the inductive step. Now I actually need to prove this statement. So I need to prove this statement here. So how am I going to do that? Well, I'm going to use sort of the same process I was applying here, right? Where I was saying, well, if S in n plus 1 steps using grammar G gives me some string of terminals, then what's the first production rule that it's going to use? Well, the first production rule it's going to use, it can't be S gives me the empty string, right? Because I've already, well, let's just say it's not that because I've already covered this case. So it can't be S gives me the empty string because I won't have, 2 or more derivation steps. Or I guess n plus 1, so 3 or more. Yeah, 3. Okay, so it can't be S gives me the empty string. So that's not what I'm going to consider. So the only production rules I could use on the first derivation step would be S gives me SS, and S gives me ASB, and also S gives me BSA, right? So these are the only possibilities. And what I'm going to do actually is I'm going to split this into 2 cases. I'm going to say this is case 1 and this is case 2, and you'll see in a second why I need cases. Okay, so case 1 is going to be not that hard. So if the first production rule was S gives me ASB or BSA, so if S was ASB or BSA, what that means is that S, so this S had n derivation steps left. It had n derivation steps left to produce a string of terminals, right? So S has n derivations to produce a string X of terminals, right? So that means that I have that S in n steps with the grammar G derives some string of terminals X. But by the inductive hypothesis, that must mean that X is an L, right? Because N is between 1 and N. And so what that means that for S n plus 1, where I start with either the production rules A as B or B as A, I can get the string either AXB or BXA, right? So that means that I'll write therefore in n plus 1 steps, I can either get the string of terminals AXB or BXA. Okay, and so that's because of this reason here, right? Because of this. Okay. But then what do I know about AXB then? If W is AXB, I know that X has the same number of A's and B's. So now if I just add one A and one B, of course I still have the same number of A's and B's, right? But then the number of A's is equal to the number of B's because I've just added one A and one B, right, from an equal number. Right? And so that of course implies that W is an L. And then similarly for W is equal to BXA. Okay, so this is case 1. Okay. Now what's case 2? Case 2 is if the first production rule was S gives me in one step SS. So the first production rule that I used was S gives me SS. Okay, so this is the first step. Okay. So what does that mean? That means that I have n production rules left, or I have n derivation steps left to generate a string of terminals from SS. Okay. So that means that then if I label these start variables S superscript 1 and S superscript 2, then from S1 and S2, I have n derivation steps left to generate a string of terminals. Okay, right? So that's just what it means for the first production rule to be S gives me SS. But then what that means that each of them has to use at least one production rule, right? But each of S1 and S2 must use at least one production rule, right? Right, and namely, it could use S gives you the empty string. So therefore, SI will have to generate a string of terminals using the grammar G in, let's say, T steps, where T is at least 1. And now it's not actually at most N, it's at most N minus 1, because I have N plus 1 derivation steps total. I've used the first one for S gives me SS. Now I have N remaining, but I know that each of the start variables uses one production rule. So that means that for SI, I need to use at most N minus 1. And so now, hopefully you see why I had to sort of add this, this base case of N equals to 2, because if I had the case where N was 1, then I have T is between 1 and 0. And then that's not really, strictly speaking, a problem, but then you would have to sort of make your inductive step even more edge casey, and that would make it slightly less elegant. Okay. So for N equals to 1, you get, T is between 1 and 0. And so to prevent that, I just said that let's show that it's true for N1 and 2 so that I don't have this edge case. Okay. So then I know that from S, I can generate a string W in T steps where T is between 1 and N minus 1. But of course, N minus 1 is less than or equal to N. So then I can use the inductive hypothesis. So by the inductive hypothesis, let's say I'll label the string that can be derived from S superscript I, S subscript, W subscript I. So by the inductive hypothesis, both W1 and W2 are in L. So then that means that from S in n+1 steps, I get the string of terminals W1, W2, right? But because W1 is in L, it has the same number of A's and B's. And because W2 is in L, it has the same number of A's and B's. So if this is equal to W, then the number of A's in W is equal to the number of A's in W1 plus the number of A's in W2. That's just what it means for two strings to be a substring, two substrings to complete a string altogether. And then because both of these strings are in L, that means that NA is equal to NB in both cases. But now the sum of the number of B's for W1 and W2, that's equal to the number of B's in the string W altogether, right? And so of course that means, right, so therefore W is in L. Okay, and that shows the inductive step. Good. So I wrote on this page at the bottom right, 9:05. It's 9:30. But it's okay. It's a very important example. Okay. Any questions about this direction? No? Really? It was that clear? Or people are just confused? Owen, yes. Right. Yeah, no, yeah, okay, I see. So the question is, well, what if, very good. The question is, what if both S superscript 1 and 2 use n-1 derivation steps? Well, that's not possible because then you would have 2n-2 derivation steps. And you can probably show that that's greater or equal. That's strictly greater probably for n is 3 than n+1. So that's not possible. The only thing you really need, but that's not even that important, because really all you need to do, really, what I'm doing in the inductive step is I'm trying to get to the inductive hypothesis. And all I need to be able to use the inductive hypothesis is I need a guarantee on the bound for T, right? Once I have that, then it's okay, then I'm good. Yes? Yeah, sure. Yeah. So the question is, why is this n-1? Well, that's because I know that to start with, to begin with, I have n+1 derivation steps, right? But now here I've used 1, right? I've used 1 to get SS. So I take away 1. So now I'm at n. But now both of these S, from both of these S's, I have to get strings of terminals. So that means that this one has to use at least 1. So then that means that I have to take away at least 1. So I have n-1. Yeah? Oh, this? Oh, that's just to say, well, that means that I can use the inductive hypothesis because n-1 is less than or equal to n. Yeah, last time I checked. Okay, good, excellent. 9:31. So, okay, so what I'll do the other direction, but I'll just show you what the statement P of n is, and I'll post the notes for how to prove it. Because otherwise, we'll have spent all class doing 2 exercises. Prakash would not be proud. Well, actually, maybe it would be. I don't know. Who knows? Okay. So I want to show now that if a string is in L, then it must be generated by G. There is some derivation for the string W. And so to do this, I need to make another claim that depends on some integer. In this case, the integer is going to represent the length of the string. So the claim in this case, I make a claim P of n, which says that if a string is an L and that string has length 2n, so of course n here is a natural number, then W is in the language generated by G. And so again, notice that I'm using the length of W is 2n. I don't lose any generality because if W is an L, then it must have the same number of A's and B's, and so its length must be even. So I lose no generality by stating this instead of just n. Okay. And so then to prove this, the proof is again by strong induction. But in this case, it's on n. Okay. Very good. So I'll post the notes for this because otherwise, post the notes, but I'll say try as an exercise. Try as an exercise. So if I say this, then I feel less bad that I'm not covering it in class. Okay. So there's an extra note here that I've written in red, and it says that you know, it would be a shame in a theoretical computer science class to have no induction proofs on a test. Okay, good. Moving on. So now that we've shown how to prove that a language is context-free, and so this technique can sort of generalize to showing that if you have some right linear grammar and you claim that it generates some language, then prove that. You can also do the, you can use the same technique of strong induction. And just FYI, in case you had a slightly more complicated grammar, so in case you had multiple variables, right? Because in this case, we only have one variable. And in general, I'm not going to test you on more than just one variable. That would just be mean. But if you had more than one variable, then you just have to reinforce your claim in your induction hypothesis. And you need to say something like, from S in n steps, I get this form of string. From the second variable A in n steps, I get this form of string, and so on. Right, so you would have to reinforce your claim in your induction hypothesis. But so now that we know how to show that a language is context-free formally, can we say anything about whether, you know, two languages which we know are context-free, what happens when you take their union? And so we can say some things, and so that's a good segue to talk about closure properties of context-free languages. Okay, so closure properties, I'm not going to re-explain what closure properties are. I've talked about the meaning of closure properties for regular languages. In this case, I'm just going to present to you some operators under which context-free languages are closed. And so notice that at this point, we've started really just talking about context-free languages, and that's just because from the family of regular languages, the next family of languages, which is of interest in theoretical computer science, is the family of context-free languages. Okay, so that's why we're spending the middle third of the course talking about context-free languages, and then the last third is going to be about what's on the outside here. But let's stick to context-free languages for now. Let's discuss the following theorem. So suppose I have some non-empty alphabet, and I have a pair of languages of the alphabet sigma. And so this theorem says that if L1 and L2 are context-free, then so are the following. So are L1 union L2, L1 concat L2, and L1 full star. So you're probably asking yourself, well, what about the intersection and the complement? Well, spoiler alert, spoiler. Context-free languages are not closed under the intersection and the complement. But to see that, we have to discuss what a non-context-free language is. And so we'll do that in a few lectures from now when we discuss the language AN, BN, CN, which can be shown to be not context-free. Okay. But for now, let's stick to these closure properties, these positive closure properties. Let's not be negative. So how do I prove something like the first closure property? Pretty simple. So if I know that L1 and L2 are context-free, so if L1 and L2 are context-free, then this implies that there exists context-free grammars G1 and G2. which are, again, 4 tuples. So let's write them out explicitly. Such that the language generated by G1 is L1, and the language generated by G2 is L2. Okay, so this is what we know by assumption. This is what the premise of the theorem is telling us. Now, what we need to do to show this first result is we need to create a context-free grammar which generates it. Well, the context-free grammar is going to be quite simple. All I'm going to do is I'm going to say, take the mechanism of G1, take the mechanism of G2, and now allow this grammar G prime to either go to G1 or G2. So this is a similar idea to showing that regular languages are closed under the union. So now consider the context-free grammar G prime, which is going to be a 4-tuple V prime, S prime, sigma P prime. So notice here that I've just sort of assumed that the set of terminals is just sigma, right? And that's a natural assumption to make. So consider the following context-free grammar G prime, where V prime is the union of the variables from G1 and G2 plus some extra star variable S prime. So this is going to be a special star variable S prime, and it's going to be the star variable for G prime in particular. And P prime, so P prime is going to be P1 union P2 union, and now I'm going to just add 2 new production rules. I'm going to add the production rule S prime gives me S1 and S prime gives me S2. Whoops, come on. Okay. And so this, it turns out, so consider this context-free grammar. G prime generates L1 union L2. I'm not going to prove this formally, but it should be clear why. If you take some string of terminals which can be generated by G prime, then either from S prime, G prime went to S1 or S2, and then from S1, you can only generate strings in L1, and from S2, you can only generate strings in L2. So that shows one direction. And then if a string is in the union of either of the languages, well, if a string is in the union of L1 union L2, then either it's in L1, in which case you can derive it from S1, or it's in L2, in which case you can derive it from S2, and that's covered in both of these cases, right? So that shows that context-free languages are closed under the union. So a question for you, what about the infinite union? There's a review exercise on this, but I'll ask it here again, and I'll leave this as an exercise for you. Okay, good. So maybe let's do one more. So this was one. Let's do the second one. Let's do the concatenation one. So if I know that L1 and L2 are context-free, how can I show that L1 concat L2 are context-free? Well, it's going to be a very similar idea. So I'm going to actually copy most of the proof from here, most of this setup, and I'm just going to slightly tweak it. So all I need to do now, is I need to show, so I'm showing, remember what I'm trying to show is I'm just trying to show that L1 concat L2 is context-free. But to do that, it's also not that hard. Just say, create a new grammar G prime, where the start variable S prime goes to S1, S2, right? And then from S1, you can generate some string in L1, and then from S2, you can generate some string in L2. Okay. So the setup is exactly the same, except that now, instead of adding 2 production rules, I only need to add 1. And it's going to be S prime gives me S1, S2. Okay. Okay, and then we can, it can be formally shown, but hopefully it's immediate enough that G prime generates L1 concat L2. And for L1 star, I'll leave this for you to do. So this one is for you. And I'll put a smiley face. Okay, good. So the time I wrote on the bottom right here was 9:15. 9:45. Okay. Not too shabby. So I think to end today's lecture, I will finish with an example, and I will start Tuesday's lectures with left and rightmost derivations, as well as parse trees. So I'll do that on Tuesday. And so to end today's lecture, I'd like to give you one final example. And so what I'm going to do is I'm just going to concretely illustrate some of the ideas I just used here. Okay, because this is quite abstract, right? I'm just talking about some arbitrary context-free grammars J1 and J2. But let's make things slightly more concrete in case things aren't clear enough already. Okay, so the question here is going to be to give a context-free grammar G, which generates the language L, AN, BM, CK, where either N is equal to N plus K, so the number of A's is equal to the sum of number of B's and C's, or K is equal to N plus M, so the sum of the number of A's and B's is equal to C. And so what's going to happen is I'm going to actually use some of the things I just used in the previous proof in this exercise. So some of the tricks and techniques I just used. So hopefully this makes things a bit more concrete. Okay, so how can I do this? How can I generate a grammar G that does this? Well, I know that I have two cases. So what I can just say to start with, I can just say that my grammar G has a start variable S, and it either goes to S1. S1 is going to cover case 1, or it can go to S2, where S2 covers case 2. And then from S1, I need to generate a string that looks like AN, BM, CK, where this is true. So in other words, if I replace N with N plus K, that means that my string W needs to look like A, N plus K, BN, CK. Now rearranging just a bit, that means that the string has to look like AK, AM, BN, CK. So now at this point, it's not all that bad anymore, right? Because all you need to do is you need to generate an A for a C, and do that, any number of times. And then once you're finished doing that, you generate the sort of inside of the string where you generate an A and a B at the same time. Okay? So then to do that, I'll generate the A's and the C's on the outside first. So I'll say that from S1, I can generate an A for a C, and then go back to S1. So this is going to be, S1 is essentially going to be responsible for generating the outside A's and C's. And then once I'm done doing that, then I go to the interior of the string. So let's say A1 is the interior. And then from A1, I generate an A with a B, right? So I generate an A with a B. And I can keep doing that until I terminate with the empty string. Okay. And then I can do the same thing. For case 2. So for case 2, let's write it over here. So for case 2, let's just rewrite explicitly what W is. W is AN, BM, CK, but now K is equal to N plus M. So let's just write that out. W is AN, BM, C, N plus M. Again, rearranging, this is just AN, BM, C, N plus C power M plus N. And then this is just AN, BM, CM, CN. So again, it's going to be the same idea. I'm going to match the A's on the outside first, and then the B's on the inside second. So I'll do that from S2. So from S2, I can generate A and C on opposing sides. I can do that any number of times. Once I finish doing that, I go to A2. Then at A2, I generate B's and C's on opposing sides any number of times. And then once I'm finished doing that, I terminate. Okay. So hopefully this gives you a better illustration of this abstract idea of how to compose grammars. I'm sort of using the same ideas here in this exercise here. Yes.
What does it cover the both?
If it covers both, so the question is, how does it cover the case where both are in, so when the case that n is equal to n plus k and k is equal to n plus m. So there's a few things that I'm thinking of saying. It's a bit tricky to answer this question without getting sidetracked. Can we talk about that after? Yeah, okay. Because it's an involved answer. Yeah. But I can also post let's because it's an important question. So I'll post something after. So I'll post what happens if it's both. Okay, it's a good question. Any other questions about this? Okay, I have 5 minutes. I'm going to use the 5 minutes to introduce what I wanted to talk about. It's nowhere near enough time to fully discuss left and rightmost derivations as well as parse trees, but it's a good start. Okay, so so far, when we've been talking about the language generated by G, we've been talking about what strings of terminals can we get from S using sort of any number of derivation steps. Now, it turns out that there are alternative ways of talking about L of G, of talking about the language generated by G, which are equivalent, but which allow us to sort of discover phenomena which otherwise would have remained sort of invisible, more or less. And so to do that, to discover these phenomena, we need to discuss equivalent definitions to L of G. Okay. And so the first equivalent definition is going to rely on leftmost and rightmost derivations. So in leftmost and rightmost derivations, what you're doing is you're imposing an order on which of the variables in your intermediate form should be replaced. So in leftmost derivations, you always force the leftmost variable to be replaced. And by the way, here I'm sticking to context-free grammars G. Okay, so you're always replacing the leftmost variable in your intermediate form. In rightmost derivations, you're always replacing the rightmost variable. So for example, if I have my context-free grammar, which I wrote before, S gives me SS, ASB, BSA, and the empty string, then a rightmost derivation of ABBA would be the following. So the first thing to do is to start with S and replace this with SS, right? But now, because this is a rightmost derivation, I need to always replace, whenever I have the choice, the rightmost variable. So in this case, I'm going to start by replacing this S with BSA. So I'm going to replace this S with BSA. And then again, I have a choice. If I have a choice, what I need to do is I need to replace the rightmost variable, so in this case, S with the empty string. So I'll do that here. I'll get S, B, empty string A. And then at this point, I don't have a choice. At this point, I have to replace the left S, well, the only S really, this remaining S, with ASB. So that will give me ASB, BA. And then again, I can replace this S with the empty string, so I get AB, BA. So this is a rightmost derivation. So this is a right, so RM for rightmost derivation, because whenever G has a choice, it replaces the rightmost variable. Okay, so that's rightmost. Leftmost is exactly the same, except that it's replacing the leftmost variable, right? So leftmost the leftmost derivation of ABBA would be S gives me SS. Then I replace the leftmost S with, in this case, ASB. And then again, I have a choice. I replace the leftmost S with the empty string. Now at this point, I don't have any choice, so I have to replace the only S with, okay, I have 2 minutes left. Should have said something. Damn. I replace this S with BSA. And then finally, I replace this S with the empty string, so I get BA. Okay, so, this is a leftmost derivation because whenever I have a choice, so in this case, I replace the, oh, sorry. Come on. In this case, I replace the leftmost variable. And again, in this case, I replace the leftmost variable. So that's a leftmost derivation. The last thing I want to talk about, so these are rightmost and leftmost derivations. I'll define them formally on Tuesday. The last equivalent way of talking about L of G that I want to introduce here, but which I'll talk about more on Tuesday, is the notion of parse trees. So the notion of parse trees. So in parse trees, you have a rooted tree, which is rooted at the start variable S. And the tree has nodes which represent variables of your grammar. And the leaves of the tree are the string that can be generated from the grammar G. So in this case, using the same grammar, so using this grammar G. So using this grammar G, then the parse tree, so the parse tree of G for the string A, B, B, A would be, well, you start at the root S, and then you can use this production rule to get S, S. And then from this S, you have to replace this S with A, S, B. Then from this S here, you use the empty string production rule. And then for the S on the right, you replace S with B, S, A, and then replace this S with the empty string. So then this thing here, the collection of leaves of the tree, this is called the yield of the parse tree of G. And so on Thursday, we'll see that the language generated by G, which we defined as the string of terminals that can be derived from S, that's the same as the string of terminals that can be derived from S in a rightmost fashion, which is the same as the string of terminals which can be derived from S in a leftmost fashion, which is the same as all of the yields of the parse tree of G. Okay, so all these representations for L of G are equivalent. Okay, that's it. I won't make you torture you more than that. Thanks very much. Have a nice weekend, and good luck on your midterm, if you have one.